The most remarkable achievement of the coming word in theoretical physics would be to come up with a valid theory of quantum gravity, or a proof of those that claim to be one. Currently, we have the quantum descriptions of all of the known matter particles and three of the four fundamental forces of nature. That is quantum electrodynamics for the electromagnetic force, quantum chromodynamics for the strong nuclear force, and the electroweak theory for the weak nuclear force. These are known as quantum field theories, and the combined formalism of these three forces and all of the known matter particles is known as the Standard Model, except for gravity. But for gravity, we have a rather more astonishing theory, general relativity. It describes gravity not as a force, but as an illusion created by the curvature of spacetime. But we know that either of these theories cannot be the whole picture. Standard model is incomplete without gravity, and general relativity breaks down at small length scales. That means quantum mechanics and general relativity does not, as of today, work together. Quantum mechanics does not describe gravity, and gravity breaks down at quantum length scales. So there's a problem, but luckily we have a solution, or unluckily the solution has its own problems. String theory offers a compelling picture to not only merge general relativity with quantum mechanics, but also to describe all of the other known matter particles and forces, a theory of everything. Even more is that it predicts new, currently hypothetical particles called superparticles. But more about those in later episodes. In today's video, we are talking about how string theory unites general relativity with quantum mechanics. The problem with merging general relativity with quantum mechanics in the conventional quantum field theory is that in these theories, the elementary constituents of matter and forces are point particles, and the interactions between 2 point particles happen at a single point, which is kind of the problem. When all of the energy of the interaction is focused on a single point, it gives absurd predictions, like infinite probabilities. In the quantum field theories of the other forces, these infinities can be removed using a method called renormalization. But with gravity, it does not work. General relativity works on the principle of smoothly curving spacetime, but in ultra-microscopic length scales that are smaller than the Planck length, due to the uncertainty principle of quantum mechanics, spacetime becomes highly turbulent and catastrophic. This causes general relativity to break down. This is important to note that outside the Planck length, general relativity works fine. Only when the length scales involved are below the Planck length, general relativity breaks down. So how does string theory change this picture? Well, let's start from the basics. The fundamental idea of string theory is that particles that we previously thought are elementary and are point size are neither elementary nor point size. They themselves are made up of tiny vibrating one-dimensional strings. And they are not point size but have length. And the different ways by which a string can oscillate or vibrate manifest itself as different particles. These strings are very small in size. They oscillate in the smallest possible region of space, the Planck length, and that is why we were not able to observe these strings. They were just so small for anything we have ever made. The reason why string theory is able to merge general relativity with quantum mechanics has to do with strings themselves. Unlike in the case with point particles, strings have length, and thus they smear out the place where the interaction between two strings has taken place. How does this smearing happen? Well, in the case with strings that have length, different observers will measure slightly different locations in space and time where the interaction between two strings has taken place. That means the interaction location is smeared out on all of them. This dilutes the ultra-microscopic properties of the place where the interaction has taken place, as different frames of references observe slightly different places and times of the interaction. Thus, it kind of allows us to ignore the ultra-microscopic weirdness happening in sub-Planck length scales and gives us finite answers as expected from a sensible theory. This does not happen in the point particle theory, as different observers still measure the interaction location to be identical. In all of quantum field theories, forces are mediated by elementary particles. Same with the elementary particle associated with the gravitational force was termed the graviton, a hypothetical particle which is ought to be responsible for mediating the gravitational force in theory. In string theory, there is a particular string vibration that matches exactly with the properties we expect from gravitons. The difference being, in quantum field theory, graviton is an elementary particle, whereas in string theory it is a particular type of string vibration. So here it is. This is how string theory unites general relativity with quantum mechanics. We were not able to come up with a valid theory of quantum gravity because we had assumed that elementary particles are point size, but there is no particular reason to believe that they should be point size. Now there is one more thing that we should all remember, and that is string theory currently have their own different problems. Extra dimensions, superpartner particles, and problem of lots of choices to choose from. We'll talk about these in upcoming episodes if everything goes well. But one thing is clear, the extended nature of string allows us to smear out the interaction between gravitons and thus removes the infinities arising from sub-Planck length spacetime. In theory, strings are indivisible. There is no supposed substructure to these strings. And in string theory, we cannot probe distances shorter than the Planck length. Why? This is what we'll talk about in an upcoming episode. But for a moment, just think about it. If we cannot probe distances shorter than the Planck length, can we say that they even exist? And can this new insight tell us something about Big Bang or black hole singularities? Think about it. Do tell me if I was wrong about any of this because this video is based on my own research. If you have something to ask, you can ask in the comments. And thanks for watching. Bye.